At the moment, the address decoding on the BSX is via a 74C139 logic chip. If you look at the truth table here, there are two inputs going into it, memory request and A15. I'm going to be implementing this logic in the GAL. So, starting with the ROM select. If memory request is low and A15 is low, we want the ROM chip select to be low and the RAM chip select to be high. It's a similar situation with the RAM select. If memory request is low and A15 is high, we want the ROM chip select to be high and the RAM chip select to be low. So how does this translate to the GAL? GALs are programmed in a low-level language called GALasm. This makes coding fairly straightforward, as long as I can phrase the problem correctly. There's a utility called GALasm that translates this human-readable text into a format understood by GAL programmers. In this instance, I'll be using my trusty TL866II EPROM programmer. I understand that this programmer can flash GALs. If you have an earlier model or a different brand of EPROM programmer, then your actual mileage may vary, depending upon the brand of GAL. To define the logic in GALasm, we first label the pins. The 22V10 has 24 pins, which comprise of 12 input-only pins, 10 pins that can be input or output, power and ground. It is worth noting that if any of the outputs need to be clocked or latched, then pin 1 is the clocking pin. Similarly, if any of the outputs need an output enable, then pin 13 is the output enable pin. All pins have an internal active pull-up connection. We'll not be needing latching or output enable, as this is just going to be used for address decoding, so we will label up a memory request, an I/O request, and some address lines on the inputs. For the outputs, we will assign a RAM select and a ROM select, and the unused outputs we will label as not connected. We can then start implementing the logic table. On line 7, we want RAM select to be low when memory request is low and A15 is high. And on line 8, we want ROM select to be low when memory request is low and A15 is low. Note the slash character denotes not, star denotes and plus, which we're not using it, denotes or. Finally, I need to declare which device I'm using, in this case a GAL 22V10. I can then run the GALasm utility on this PLD file to generate 4 ASCII files. The aptly named .chip and .pin files are useful for documentation and detail the pinouts of the GAL and whether they are programmed as inputs or outputs. There is a .fuzz file, fuse, which shows the states of the bits in the logic matrix. And finally, there's a .ged file, which will be used to program the GAL. I've connected my EPROM programmer to my PC, and I'm now ready to program the GAL with the GED file I created earlier. First, I need to select the correct device. I better double check the label on the chip. It's quite difficult to read. Get my magnifying glass. It's an Atmel ATM 22C V10C. So let's select that in the software. you go, select GAL, 22V10, filter by Atmel, 22V10C. Great, it's in the database, that's a good start. Now we need to check the device info to see how we insert it in the programmer. So the chip goes at the top, notch at the top. That's fairly straightforward. I think that's correct. Lever down. Do a blank check first, just to check that the programmer can see the device. Device, blank check. That's looking good. The next step is to load up the JAD file. That's the fella. So if we scroll down, it's all zeros. Should be some ones somewhere, hopefully. There we go. That looks like my logic, but it looks like some logic anyway. But technically it looks like just ones and zeros, but I assume that is my logic. So the final step is to program it. So here we go. Fingers crossed. Looking good. We can just do a verify now as a belts and braces check. Verify error. Okay, that's interesting. It passed earlier though. I'll pause video and then find out what's going on here. Okay, I'm back again now. Had a quick look online. It looks like it's something to do with the verify function of the XG Pro software and or the TL866. But it seems to have programmed okay, even though I can't verify it. And bizarrely, it seems to have passed the verify on the programming dialog. So I think the next step is for me just try it and see whether or not it works. So now, the build montage. And we're done. All I need to do now is throw a voltage at it and let's see if it works. You'll have to excuse the rather Heath Robinson wiring here, I'm afraid. I couldn't find the wires for my power supply. It turns out that Houston, we may have a problem. Nothing is happening. I'm not getting any activity at all on the 22V10. Perhaps I shouldn't be surprised about that, given the fact that I couldn't verify it or read it. I think the next step will be to go back to the programmer to see whether or not I can actually program this and get it to verify correctly. I think I'll hit the internet as well to see whether or not there are any other suggestions. I have been led to believe that this should work. Unfortunately, it doesn't seem to. So finally, we have some success. We have blinking lights. Well, lights. it turned out that the verify fail that I had earlier wasn't a false alert. It was simply that the device wasn't being programmed by my EPROM programmer. Thankfully, a software update and a firmware update fixed that. I am now running XG Pro version 10.3.1, which helpfully updated the firmware on my programmer to version 4.2.118, and that seems to have done the trick. I can now program the device correctly, and if I read or verify it, I can see the contents with no issues whatsoever. So let's check whether or not my logic works. I've got the truth table on screen that we're trying to emulate, and if you can see here, I've got a dip switch. Switch 2 is unimportant. Switch 1 is memory request, and switch 3 is A15. So let's see if this works. If the switch position is on, it's being pulled high by these connections here. If the switch position is off, I've got these pull down resistors here, so it'll pull the signal low. So at the moment memory request is high. So looking at the first line of the web page, I would expect Y0, which is the ROM select, to be high, which is this, it's lit, and I'd expect RAM select to be high. So both of these LEDs are high. That's ROM select and that's RAM select. Perfect. So let's switch memory request to low. So at this point the Z80 would be requesting memory from the RAM or ROM. See, one of the lights has immediately gone off already. A15, or switch position 3 in our case, is low. So we would expect at this point Y0 to be low, which it is, the LED is off, and Y1 to be high, which it is, the LED is on. Perfect. So let's try and access the RAM. So A15 now goes high. So ROM select has gone high. So at that point it'll have deselected the ROM, and RAM select is low, which is fine. It will have selected the RAM at that point. So I think job's a good one. I'm really happy with the ease of programming this GAL. Next step is to integrate it into the BSX. Okay, the moment of truth now. I've put the GAL onto the breadboard for the BSX. This is the 74 series logic chip that it's going to replace. This is currently doing the address decoding for the RAM and the ROM. You can see these two lines here going to the RAM chip and the ROM chip, their respective select lines here, and back in there somewhere. I've given it power, and I've given it ground, and I've already wired up A15, which is going to the makeshift address bus over here. This is A15, and I've wired up memory request here, because that wasn't previously there. So I've got 4 control lines here. I think that's IO request, one of those is read and write, and then that's memory request. So the next step is to take these address lines and just move them up to here and here. So first I'm going to take the RAM select line. So this is the RAM chip, so that must be the RAM select line. So let's unpick that. Do these one at a time so I don't get them mixed up. And RAM select goes to pin 14 of the GAL. So let's just move that temporarily over to there. There we go. Tidy up the wiring later. That's RAM select done. ROM select similarly. Let's unpick that carefully. Move that over to here. That's not going in. There we go. Tight. So we've got A0 RAM select. Just double check. It's going to the RAM chip. ROM select. Definitely going to the ROM chip. This is still running, but it's not connected to anything meaningful, so I can leave that in for the moment and remove it later at my leisure. I figured this was a good way of doing it because I could, if this wasn't working, quickly roll back to using the 74139 chip down here whilst I was debugging the problem. I continue to use the BSX. So we've got the USB plugged in over here to the blue pill STM32. This is actually providing power for the board as well as some I/O. So I'm going to plug that into my computer now. There we go. I haven't got a proper reset circuit in here, so I'm going to hold the reset. There you go. You can just about see if I adjust the brightness. We've got something on the screen there. So let's see what's happening on putty. Okay. So you've got putty on screen there. I'm going to give the BSX another reset. There we go. Seems to be working. Fantastic. Let's give it a quick shake through, work out what's going on. So let's do a memory dump. Seems to be working okay. Disassembler's working fine. Let's just try a quick basic program. I've got BBC Basic loaded on here as well. The Z80 version modified for the BSX. So that's launching fine. There is a bug in this where it flags an escape first time round, but we don't worry about that. I've not loaded the fix to the ROM yet. Okay, I think jobs are good, and I could do a memory test at some point to try and work out whether or not it is addressing all of the memory correctly, but it seems to be flicking between the RAM and the ROM okay there. I'm going to call that job done. I hope you've enjoyed this video. If you like it, then please subscribe to my channel, and you can also bob over to my webpage breakintoprogram.co.uk for more information on what I'm up to at the moment. Thank you.